End of class.
Hold on, me.
If you want to draw on the board, it has to be before the bell or after the bell, or at the end of class in this case, because we'll have time. Okay. All right. Angle bisector theorem. Now this is really the triangle angle bisector theorem. That's why I drew that piece of poop over there, which is really a triangle. So triangle angle bisector theorem. This only works for triangles. It doesn't work for just any angle. An angle bisector theorem is something different. That's when you have an angle and it's bisected. Then you know that any point on that line will be equidistant from the sides. That's something different that will prove. Oh, sorry. That's something different we'll prove. Any point in this line will be the same distance from both sides, right? The triangle angle bisector theorem says this. If you have a Cevian that cuts one of the angles of the triangle in half, right, it bisects it, then the opposite sides here will be proportional to the bases. Now, you think proportionality, you think, oh, similar triangles, and you'd be right. But here's the problem. There's no way to prove these two triangles similar. No way to do it. In fact, they won't always be similar. In fact, most of the time they won't be. So how do we get something like this? Well, the answer is going to be we're going to draw an extra thing in here, prove those triangles similar, and then use something with the relationship between those two triangles, yada, 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 okay? So the key is going to be drawing a parallel line. Yeah?
Well, I have a question, because like, I know it doesn't really go with what we were learning. Like,
That's fair. What do you got?
But like, we could do a linear pair theorem with the CV and CD, and then we could create like two different angles, and then we could have.
So with linear pair, it doesn't mean that these two are congruent, though, right?
No.
It means that they add up to 180. We need them to be congruent to do double angle.
Oh.
You see what I'm saying?
Yeah,
Yep.
yeah.
Now, when will they be similar? When they're both 90, right? What's up? Take this too?
Oh,
Did we review for it? You mean like take it for the first time or take a version 2? Take it the first time? Yeah, I can do it too. Right. So no way to prove that these are similar. In fact, they won't be unless these are both 90, and that's just not going to happen. We need something more useful than that. We need something that works for any two triangles if we have a bisector at the top. So angle bisector theorem. We're going to prove it. We're given that this bisects, so that means we get this. These two angles are congruent, right? That's what we get from here. We're on page 7 now. Page 6 was just to show you the theorem. I know, silly. And now we're going to prove that x over y equals a over b. So the first thing we're going to do is we're going to add something to this diagram. We're going to draw a line that's parallel to AB. So I'm going to bring out my ruler and doing the bestest I can, I'm going to draw a line that's parallel, so it says me, to this line. And I'm going to call this line CQ. And I'm also going to extend this Cevian, this angle bisector, until it hits this line. And you'll notice what that creates, I'll call that X, is another triangle. So we're going to say let CXQ exist and let ADX exist. Now remember, if two line segments have the same point in them, that means they must intersect there, right? They must share that point, so they intersect at X. That's why I wrote both of those.
He's a leprechaun.
All right. So now that I've created those, what do you see? There's a really efficient way of doing this. We want to get this triangle similar to another triangle, so we're going to need some more angles. There's an efficient way of doing this, and there's a not efficient way of doing this. We're going to do whatever you see first, and then I'm going to show you the efficient way, okay? What do you see now that we have parallel lines? What do you see?
Rescue paper.
Wait, are you able to do vertical lines theorem?
Vertical angles?
Yeah.
Where do you see it?
On the x. Like,
Here and here?
No.
Or here?
Yeah, right there.
Yep, you could. That's not going to be very useful, though. It's true. They will go together. I guess it could be useful, but I won't mark it.
Oh.
It's going to take us way out of left field. Well, if we have two parallel lines, we should be looking at transversals and trying to find corresponding or alternate interior angles. Yeah?
Yeah, angle DAB could be like corresponding to angle.
Whatever this is?
Yeah.
Darn it. I knew you guys would see that. All right, so that's not the most efficient way of doing it, but that's true. So you're right. These angles will be congruent by cap, right? This angle right here. And then by vertical. Another way you could do that is say alternate interior. You guys see it? They're inside the parallels, and they're on opposite sides of the transversal. So those two angles are alternate interior. So I'm just going to forget this, and I'm just go straight to the chase, alternate interior. Okay? Angle DAB, don't you dare. Congruent to angle CXD. Cool, cool, cool. So we've got one pair of angles for all these guys. What else do you see? We need another set of angles. Or, let me see. Can I make it more efficient? Yeah, we need another set of angles. When?
Can you do CDX and CDA?
So these two angles?
Yeah.
So you said CDX and CDA. That's this angle here, CDX, and CDA is this angle here. Those two? We can't do those because we don't know. It's a linear pair, but it could be like 180, right? We don't know that they're congruent necessarily. If they were congruent, then they'd have to be 90, but we don't know that. Yeah.
You can do vertical angles at ADX and
AD,
no, it's a little A, like CDX, sorry.
CDX, and what? So CDX and
ABD.
ADB? Yep, okay. So these angles are congruent by vertical. And now we've got two angles to prove these two triangles similar, right? You could have also done alternate interior here. You see that? Transversal, two parallels, opposite sides. See that? So we could have done that. But that's fine. We got it done. So we're going to say by vertical angles theorem. You guys are pretty efficient. Well done. Angle CDX. Remember, we use capital letters for our angles and everything and little letters for segments, right? For segment lengths. And ADB. Little letters are variables. All right. So now by AA, we have two triangles that are similar. This triangle and this triangle, right? So by angle-angle similarity, you guys never tell me when you can't see stuff. That's why I always have to check. Triangle ADB. We'll do ABD. How about that? Similar to triangle. All right, so A is this red angle down here in this triangle. What angle will it go with on this triangle? X. And B is the unknown angle in this triangle. So it's going to go with C. So you can use CSP to prove they're congruent too. Right? And then D will go with D. Cool. Before I do CSP, what do you notice? What do you see now? Big brain play. Gotta think big picture.
It's a diamond.
It is a diamond. That's true. Right, we can connect this up and have another diamond, right? I don't need to draw any more lines. What do we have now that we've got all these angles? Don't be afraid to take guesses. I'll tell you if it's efficient or not. Yeah.
Linear pair theorem.
Here and here?
Yeah, well, that or the same area, but like with a different, that one.
So these two. Yep. So these angles would be congruent by vertical angles. That's true. We don't need that, but yes. If I were to draw another triangle over here, I could get these two similar, right? That's true. That's very true. It's kind of interesting. It's because we have a parallelogram going on here. We'll learn about that a couple weeks from now, maybe after, beginning of quarter 4. Quarter 4 is going to fly by. What do you see now?
A large triangle.
Yep. It's a big boy. What kind of triangle?
Obtuse.
I mean, maybe. The way I drew it in this one is. It's what? Yep, Isosceles triangle theorem, converse. We have the angles, we get the sides. So this side right here must be congruent to this side right here by Isosceles triangle theorem converse. AC is congruent to CX. That's these two sides, here and here, because the angles are the same. So that big triangle is isosceles, right? If we have the angles and get the sides, it's the isosceles triangle theorem converse. Good. So now I'm going to do CSP with those triangles here and here. And you're going to notice something. So I'm going to do CSP with these guys real quick. AB over XC, BD over CD equals AD over XD. Right? All right, we need to get small letters. So if these two segments are congruent, if AC is X, isn't CX also going to be X? They're both going to be little x. You guys see that? How they're congruent, so they're both going to be little x in length. Katie, are you alive? Okay, just want to make sure. So that's x, and this is x, right? They're both x, because they're congruent. So I can substitute those. AC, I can substitute x. XC, I can substitute x. AB, I can substitute y. BD, I can substitute little b. CD, I can substitute little a. So here's what I get. AB is little y. So I get little y here. XC is little x. BD is little b. CD is little a. AD, that's nothing. I don't care about it. And I don't care about XD either. Too much happiness. So I don't care about this guy. Because look, I've got what I want, right? What I have to do to make it look like the top? Flip both sides, right? As long as you do both sides, it's fine. Ta-da! So our whole point was to show, since these triangles are similar, they have shared angles, right, or congruent angles. That means this is isosceles, so these sides are the same. And so by CSP, x here will be the same as y, right? They'll relate the same way. And that's the idea. How do we feel about that? Draw a parallel, extend this, verticals, alternate interior here or here, doesn't matter, right? One way or the other. And then you get double angle to get these similar. If they're similar, then we can do CSP, right? And we can switch out their letters. You wouldn't have got X for CX if you hadn't noticed that this was a giant isosceles triangle though, right? Because those have to be the same for that to be X as well. And so when you have CX or XC, you can replace it with X. And you win. If we don't feel 100%, that's fine, because it's brand new, right? But do you feel like this is doable, right? With a little bit of practice, a little bit of looking at it, right? Not the hardest proof we've done by a long shot, not even this week. It's weird because you have to draw something in, but remember, weird is temporary, and then it becomes normal. How are we feeling? Okay? All right. So next week, what we're going to do is we're going to prove things like angle bisectors and perpendicular bisectors and all that stuff. Well, not perpendicular bisectors. but medians and all the other Cevians that we have, that they're concurrent. We're going to use Ceva's converse to do that. So we're going to prove that A over B times C over D times E over F equals 1. And then by Ceva's converse, they must be concurrent. Concurrent, not congruent. Sorry. And that's what we'll be doing next week before we take our quiz. Our quiz next week will be over all this stuff and basically the triangle centers. So it would behoove you to review the triangle centers over the weekend and then come in and retake this quiz that you bombed. And then you'll be really good for the quiz next week too, right?
If I passed.
So, quarter's ending soon. Make sure you get your retakes done before it's too late. You got to give me time to grade it too and review with you, right? That's the goal. Okay? Mark, if you want to do the world, go ahead.
I can show you the world.
Okay, it starts.